Quick question about AX on there.
AX.
Yeah, why is 5K and AX?
Good catch, because I made a mistake. Excellent. Which way should AX be going? Yeah. Excellent. Good job, Ben. I'm just writing the moment that I used. I should write this.
Is CY, it says that they're 5.966, right?
CY.
CY, oh, when you calculated it.
Yeah. 5.4166. That's a 4. Actually, let's get the real number. I'm getting a different number now. Dyslexia or something. Do it again. Yep. So it's not 8.5, it's 5.833. That process. I mean, mistakes can be made in that process. I make mistakes, but as long as we got it down, like how to get those, that's important. So then to solve the truss, this is a truss, right? How do we know it's a truss? All the forces are at the joints. That's one reason. Straight members. That's another reason. There's one more. Made out of triangles. Yeah. So it doesn't have to be a right triangle, right? It can be any kind of triangle. So this is structurally sound. It's stable when it's like this. And our method of joints works. We can use it. Okay. If you stick one force in here, like in the middle of a member, then it's a frame and we can't use the method of joints. We actually can, but we have to use other systems too. So yeah, it's a truss. Perfect. So then method of joints says, hey, isolate joints. Just draw individual joints and put those things in equilibrium. You can actually start anywhere you want on the truss, but since it's going to be a concurrent system, right? All the forces going through one point, you only have two equations, because there is no moment, so there's no third equation. So you can only have two unknowns. So don't start at a connection that has more than two unknowns. This one's pretty easy. How many unknowns are here? How many? Two, right? There's two members and I don't know their force. That's what I mean when I say unknowns. I know this, right? So I know one, but there's two unknowns. What about up here? I see. Where's the third unknown? We know the 10, we know the 5, we don't know A, B, and we don't know B, C. And that's not a member, that's just a dotted line that I put in. So there's two unknowns. Okay. How many unknown at A? Two. Yeah. It's good to be able to think through that just by looking at the connection, like how many unknowns are at these locations, right? So if I look at this, and you can do this without ever doing a calculation, right? How many unknowns at E? 1, 2, 3, 4, correct. Get it? How many unknowns at G? There'll be two once I figure out that reaction, right? So that's what I mean by don't start like, hey, I'm going to start at E. Like, oh my gosh, there's 4 unknowns there. You don't know anything about E. You can't start there. Okay. So just kind of think about your starting point. A lot of times your starting point is down here at these reactions because we know things and they're simple sometimes. Like I would start here because there's only 3 total I would start here because there's only 3 total forces. This would be fine, but there is 4 forces. So it's just a hair more complicated, right? So pick an easy spot. I would not start up here because the 2 unknowns are both at an angle, right? They're both at an angle. So that makes it more complicated. When you have an unknown on one of the axes, either the X or the Y, that makes it a little simpler because I can look at this and say, oh, that Y component of BC has to be equal to the Y force here. So if you can see that and make those decisions, it's a little easier. So I'm going to draw C. You can draw C. So draw joint C and try to figure out the directions of the 2 unknown. Right? We know this one is up. 5.41. Oops. Dang it. Where's that happen? How's that happen? 4166. And then we want to label them. You can label it CB or BC, however you want to do it. And then put in everything that you know. And if you need to find an angle, find the angle. We need that angle. And I can get it from up here. Right? So there it is. Joint C, label it for me. Figure out this angle and then try and figure out these directions. I'll give you a few minutes. All right, so I got an angle of 32. I just did the inverse tangent of 10 over 16, opposite over adjacent to get that. All right, let's think about these directions. Which way does BC go? BC point into the point or does it point away from the point? this being the point. What do you think? How come? Yeah, it's got to oppose this, doesn't it? If this is going up, then this component must come down. Right? And if that component comes down, then this component must go over. So the two components of BC have to be down and to the right to oppose this thing. So BC must point into the point. So the rule is if it points into the point, it's in compression. So I'm just going to note that right away. Which way would AB go? Is there any other X force? Careful. What about BC? BC has X effect going this way, right? Yeah, AB's got to oppose that. So don't go back to this thing. This thing's gone. When you're doing this thing stands alone, right? So don't think about this stuff over here.
How would I know?
Here?
Yeah.
So we know this goes up. So that has to do what? It's got to go down, right? So that's how I know. That's how I know which way BC goes, because the only way the two vectors can add together is tip to tail. BC's got to be here. Agreed? Okay, so now that you know that, and that, now you know AB has to oppose that component and it go that way. So I figure it all out from looking at this, not any other part. Don't go looking at other joints because they do not affect this joint. They actually do, but you can figure it out from that joint. Okay, it takes some practice to do that. All right, so that's good. So now we know this. What is that component coming down? Has to be 5.4166. And that's so the Y forces equal 0, right? Looking at this. And I cover all this up because we don't want to be distracted by it. So now that I know BC's Y component is that, and I know the angle 32, I can get the X component, right? I really don't want the X component. I don't need it. But I know that the X is equal to AB. So I do need it, right? They are equal to each other. So how do I get it? Well, if I know this one, and I know the angle, I could use.
AB is 5K, right?
Where'd you get that? Do you see a 5K right here anywhere? No. Only look here, Ben. You can't go looking around the truss. You have to stay right here at this connection to solve it. It might be. I don't know that. Okay, so let's just calculate it. So I'm going to use tangent. That's opposite over adjacent. That means I'm going to get this X force right there. So if I write tangent 32.005, and I'm using this BC triangle right here, opposite 5.4166 over, I'm just going to call it that BC X force, which is equal to AB. Those two are equal to each other. So then I know BCX is equal to, this goes over there, this comes down here, it's going to be the 5.4166 divided by the tangent 32.005. 8.667. So it's not equal to 5. Anyone else get that number? Anyone else calculate this with me? I'll do it one more time. Yeah, same number.
Did you do it in the first tangent?
I did not. I did tangent 32 equals opposite over adjacent. Tangent 32 is just a number. Right? And then to do the algebra, BCX and tangent 32 just switch places.
You did 5.1.
5.4166, tangent 32, correct. How do I solve this?
You multiply it.
You'd multiply both sides by BCX, correct? And then how do I get rid of the tangent 32? Divide both sides by tangent 32. Yeah, write it out. If you're not seeing that, like, I see it, I do it all the time, so I can just see it, right? If you're not seeing it, then do the algebra to solve for BCX, right? The rule is, if you want BCX by itself, it's got to come over here and up. This one's got to go over and down, right? So it's 5.4166 divided by tangent 32. We still need BC because we have the Y component of BC and now we have the X component of BC, but we don't have BC yet. So we have to get that. We can get that from Pythagorean theorem, or you can run a sine or cosine or whatever you want using this BC triangle. I'd probably just run Pythagorean theorem. So BC is going to equal its components squared, added together, square root, right? Yep. All right, so this joint is solved. I know BC is in compression, and I'm gonna explain that, like why that rule is that rule. And AB is what? If it points away, it's in tension. And we do need to know if it's in compression or tension. When we get to strength of materials, that's a different analysis. If something's in compression, right, forces pointing in on it, that means buckling can occur. If things are in tension where they're pointing out like this, then no buckling can occur, right? But it can just get pulled apart. All right, so as soon as I find them, I transfer them up to the truss. So BC is 10.22. And typically you write it right along its line, and that's in compression. And then AC is, oops, sorry. Oh, why did I call it? Why did I call it AB? That was dumb. This is AC. You guys let me do that. Right? This is member AC. Sorry about that. AC is 5 point, nope. AC is 8.667. Intention. This is called the truss diagram when you start putting the loads on the truss itself. So this makes good sense because we see the 5K coming in, right? This external 5K coming in here. So this must resist back. And when it does that, this thing is in compression. It's being compressed by some forces here. So that makes sense. It's hard to kind of see how this is in tension. Like, that's not very intuitive, but it is. Good so far? So far, okay. So we have only 3 members in this truss, and 2 of them are solved. We solved 2 of them from doing joint C. We really only need this member now, AB. That's the only unknown. So because there's a horizontal here, that makes this joint a little easier than this one. So I would go to joint A next. And we actually know this member, AC. We calculated it right here. So what the load is on one end of a member, the load is on the other end of the member. Has to be, because this member is in equilibrium. So now I'm going to draw joint A. And you draw joint A. So if it helps you, put a circle around it. That's what you're drawing. You're blowing it up and you're drawing only the things going on here at joint A, nothing else. Definitely put in your knowns. I kind of start with those. So when I draw AC in, this bottom one that we already calculated, right? AC points away from the joint. So it must point away from the joint here. Yep. So this is AC, and we calculated that at 8.667. So the rule is if it points away from the joint, it has to point away from the joint at the connecting end or the other end. Makes it still in tension. And then I have AB, which is my unknown. So I need its angle. Looks like that's inverse tangent 10/8. Just looking at the diagram up here, right? Getting that angle, 10/8, opposite over adjacent. I'll let you catch up. Digest it a little. Now that joint stands all by itself. We don't look at anything else to solve for AB. Put everything in we know. These two are reactions, remember. So they're not in compression or tension, they're reactions, right? They're not loads on members. AC is a load on a member. We already calculated that, it's in tension. Which way do you think AB goes? Down or up-ish? Maximus says down, AB. Anybody else have a vote? Up or down? Ben says up.
For me, I have to turn the page over here. You're on the same page. If I go back
No, go back where?
to A equals ACX equals.
No, don't. Just look at this. Don't go anywhere else. From this diagram right here, this has to be in equilibrium, right? So the sum of the forces in the Y have to be 0. Some of the forces in the X have to be 0. I just need to know if it points up or down. So then all the Y forces are going up. This is going up. What's going to fight it? Because we need this in equilibrium. It's got to equal 0. If there's up effect here, we need down effect somewhere. Right? We've got to have something coming down if we've got a force going up. And we have a force going up for sure. We know this one, right? So AB's got to go down. It's got to come down. This Y component has to go down. So these two oppose each other. I could look in the X, but there's a lot going on in the X, right? There's 5K that way. There's 8 that way. I don't really know anything based on the X. But on the Y, I only have 2 forces. This component and this force going up. They've got to be equal and opposite. That's what Newton said. So I got 4.5833 going up. I need 4.5833 coming down. I have to have it. So that is this little component right there. And from that, I know AB, I know its angle of 51.34 degrees. I know its component of 4.5833. Other component here, but I don't really care about that. From this, I can solve for AB, and I'm done. Problem solved. So I would use sine, and I would write it. Sine 51.34 equals opposite 4.5833 over hypotenuse, AB. Again, got to do my algebra. These two switch places. So it's going to be the 4.5833 divided by the sine of 51. I get 5.87. And is it in compression or tension? Remember, the rule is the points into the point, it's compression. If it points away from the point, it's in tension. What do you think, Danner? Does take a while. It takes repetition and some practice. What, Ben? Got it, you think? So I took the 587, you can't, oh yeah, you can see that. So and then I just moved it up onto the truss diagram to complete that truss diagram. So next term, what we're gonna wanna know is what is the largest loaded member, because that's the one we designed to. Normally, we're gonna make these trusses, like if they're roof trusses, even if they're bridge trusses, we're gonna use the same material throughout. It's just an easier manufacturing process than if we were like changing the size of everything all the way through. So we would pull this thing out and design this member, and then just make these the same size as this. They're all carrying smaller loads than this, so this can be our control. So that's what we need next term. All right, so I'm going to show you kind of how this whole, if it points into the point, it's compression, how that works. I'm going to draw this member BC kind of right off to the side, and I'm going to scale it down so it's a little smaller than it actually is, but that's point B and that's point C. Everyone see what I've done here? Just pulled that member out. So then I'm going to take the C point apart. So here is joint C, and here is joint B, right? So I separated the connection points, these connection points from the actual member. So this is B, right? Or that's C, sorry. It'll be confusing here. So everyone kind of get, so when we did our joint analysis, this is what we did the analysis of, joint C. And this is just a removed member BC. So you could kind of like blow this thing apart, exploded view kind of thing, right? Where the joints are out here and the members are kind of floating in space. So we found BC to be in compression, right? Everyone good with that? And compression means the arrow, the vector points into the point. So that means that this pointed in, right? And our little free body diagram of this creature looked like this, right? So here is our, that's this. And now this is the removed member. So the way this works is, oh, that means it's like in compression up there too, right? They point into the point, they're in compression. So that means that on the member itself, it's got to point in. So these two, when they come together, equal 0. And that one's got to point in. So the way the whole kind of diagram looks is this is 10.22, this is 10.22, this is 10.22, this is 10.22. Right? So if you pull the member out, it's being compressed. Equal and opposite. If you look at the joint, because when these two come together, when I bring it together, these have to kind of equate to zero. Everything equates to zero in equilibrium. That's how the rule got developed. If it points in on the member, it's got to point in on the point. So that's just why we get away with that rule. And how this becomes in compression, right? All right, so that just clarifies that hopefully a little bit. Doesn't really matter, like when you draw your free body diagrams of those connections, you know, down here, when you do that, just know that if it points away, right, that's in tension. And if it points in, this one's going to be in compression. All right. We'll do one more little thing here before I go on to the next one. You don't have to write this down. You can just sit back and digest this. All right, so just based on this drawing, I don't even have dimensions in there. I don't have anything in there, right? I mean, it's not fully defined. I will label all the points because that's good. But there's probably even more external forces on there, right? But what I want to know is BC in compression or tension? And is DC in compression or tension? Just from this diagram.
I feel like DC is tension.
So how could we figure it out just by like using our logic of, hey, everything in the Y, everything in the X?
We have 10K going to the right. Then we have to have another force opposing to the left.
Yeah, I think you're on the right track for sure. So what I would do is, and I can do it in my head, but I can also just draw it for you, is a little free body diagram of C. Right? And I don't even need to put the forces in, like the magnitudes. So this is joint C. Right? Everyone agree with that? I got this one in and I got this one in, right? So just looking at that, what can I determine? More than to the left, there's like, I don't know that to the left or right, because there's three things going on in the X, right? There's this one, and this one has an X component, correct? Anytime there's three things going on in a direction, I have no idea which way what goes if these are unknown. What about the Y direction? What's going on in the Y direction? This is going up. That's given, right? It's like 7K. This is 10K. But this is definitely going up. It's not an unknown, it's a known. So how do I got to balance that? I got to have down. The component of BC must go down. How big is it? 7K. Got to be. If the y component goes down of BC, and I know this is the line of action, then the x component must go that way. It has to, in order for BC to become a vector that has an arrowhead on it, right? So BC is in compression, points into the point. The only way I could determine that would be by looking at the y forces in my head. Like the y forces at this joint, 7K up, 7K down. That's it. So you look for that direction where there's only one unknown, right? I stay away from the x because there's 2 unknown in the x and there's 3 total forces in the x. Excellent. So now that I know that this component goes to the right, this x component, what's DC got to do? Go to the left. It DC opposes that. Those two oppose and they're equal. Well, they're not because we got 10K, but yeah. So this one, DC is in tension. Right?
What if it would be 10K going to the left?
Where?
Well, for example.
Oh, same problem, but this is going left? Yeah. So how does that change how's that change this? Right? So that's what you're saying. Okay, what would that be then? Great. I love it. The more of this we can do and see it, the better. What do you think? Yeah, BC, nothing changed in the Y. Right? I mean, X direction changed, but Y is still the same problem. We got up, we need what? We need down, and that's 7K. So then that's got to go that way. This comes this way. But now, since we got 10K and we have this unknown, which way is this got to go? I don't know for sure. Right? It depends on how big this is and how big this is, which way that goes. You got to do the math. You got to figure this out. So if this becomes, we'll say it was 45 degrees. So it's 7K. How's that? These two are both 7K because BC is at a 45. So which way has this got to go? Yep, exactly, Ben. You're getting it. 3K. That makes sense? All right, look for that one direct. If you don't have one direction where there's only one unknown, go find a different joint. Like don't do it. Because what you're going to end up with is 2 equations, 2 unknowns, simultaneous equations, which it's not in our wheelhouse, but we probably haven't done simultaneous equations in a while. It's not multivariable calculus, but it is simultaneous equations, which is something we don't want to do. So just go to a different joint where it's easier to solve and work your way to it, right? So go here. Let's look at this connection. This is a fascinating connection. I don't really want to confuse you more, but let's draw D. And this will blow Ben's mind. I can just see that coming. I love it. All right. So here's joint D. You draw it. And I'll draw it.
How would that make sense?
There's only one way it can make sense. First of all, would we want to start here? What do we know? We don't know anything. Yeah, so you would not want to start here, but let's say we started here, right? and we got the 3K pointing into the point.
We have like 3 components.
All right, are you with me? Okay, let's say we started here. We started here, and we got this at 3K. Everyone good with that? And it's pointing in, so it's compression. Right? So then that makes this what? Points in 3K. All right. Now it's legit that we go to joint D. This is BD, and this is AD. Everyone okay with this drawing? Like that is D, right? I mean, that's what it looks like. It's what we call a T connection, and actually something we look for. Like you can just look through trusses and look for these T's because they're kind of valuable to solve a truss. All right, so let's just do it. Don't overthink this. Anyone have any ideas? No, probably about this, and that's a 3. Yeah, right? AD's got to be what? 3, right? Which way's it got to go? To the right. AD equals 3K. T connections are the easiest. They're awesome. You just can roll through them, basically. What about BD? BD's got to be equal to 0. Is the only way this thing can be in equilibrium. Okay? It's called a 0 force member right there. There is no load on that member. That does not mean go up and saw them out of your roof, right? They're there for a reason. And the primary reason is at some point, somebody's going to hang material on this bottom cord that's going to have weight. And as soon as you add weight to that point, then BD gets loaded, right? If there was 1K hanging here, right? What would BD equal to? 1K going up. Yeah. So if you find a 0 force member, that just means it's 0 under that loading condition, and loading conditions change. And we're just doing a snapshot in time of loading conditions, right? We're not doing all of them. We're just doing one. But this is called a 0 force member. Now, that's cool, but it even gets better. Check this out. I'll keep it simple here. Here's another connection. Just making these up at this point. So this is joint C from some truss, right? Through the free body diagram, that's what I got. And I don't know which way AC goes, right? But I know I have 10K coming in. I knew I had 10K here from previous work at the connections next to me on the right and the connection next to me on the left. Tell me about AC. It's got to be 0. Great question. How come? We know the sum of the forces in the Y have to be equal to 0. That's one of our primary equations. And the sum of the forces in the X have to be equal to 0. If the 2X forces are 10 and 10, how big is this X force? Got to be 0, because these two already equal 0. If this is the only force in the Y, what's that got to be equal to? 0.
But if you can't have an X, you can't have a Y.
Exactly. Right. If one of the components is equal to 0, you can't have another component and you can't have a force. Yep. So T's are not just perfect T's like this, not just 90-degree T's, but they're any T's as long as these two are straight in line with each other. So like, what about this? Oh. Yeah, same thing, still zero. This has got to be zero. These are in line with each other. That's what's critical, right? So I could like flip it all the way around, put my x-axis here, my y-axis here. These two equal and opposite. This component's got to be zero. This y component's got to be zero. That thing's got to be zero. Okay. So you look for them. Don't make them. Don't make them where they don't exist. So that's what students typically do. See if I have any that, oh yeah, here's one that I haven't already drawn on. I draw on my book a lot. So like that kind of dead giveaway. But this one I haven't drawn on. So just look at it for a second. Don't say anything. But what we're looking for are zero force members. So if I give you this problem, I say, find all the loads and all these members, you're going to go, oh my God, huge problem, right? It's going to take me forever. But if we can spot zero force members, that really helps us. So don't say anything yet, but just look for, and what are we looking for? What kind of connection? T's, yeah. They got to be clean T's though. They can't have external forces. Got to be clean all by themselves. Don't say it. Don't say it. Don't say it. Anybody find one? Yes or no? Maximums did. Did you find one, Ben? No? Yes. Sort of. It's either a T or it's not. All right, good. Right? See one? Yeah. Danner? All right, where do we think it is? C. Clean T, perfect. So what is the zero force? Which member is zeroed? Yeah, this one right here. Based on that connection. Not that one. I cannot look at E and say, oh, something is zero. There's no clean T there, right? But based on C, in my head, I could draw, oh, a little force diagram of C. Looks like that. That thing's zero. Boom. Good. Now, the next good news is they can be contagious. Now that I know this is zero, I'm going to look at E. Because this is gone. So now E looks like what?
Not very functional to the brain. So
It's a T. It's that last one I showed you. Are these two in line? Is this whole thing in line? Yeah. So now E, which one's zero? BE. Remember, they can be contagious. They're not always like this, but where would I look next? At point B. And what do I see at point B? With this one gone, keep going, like follow the zero forces. Come to here, I got one going that way, that's zero. What about A now? I don't know, I got this, I'm gonna draw A, because I'm just not sure. Anytime you're not sure, draw it. And it doesn't matter the direction, and this is a pin, right? So it gets two reactions for a pin, and then it has two members coming in. That one's zero, I took it out. But is that a clean T? No, that is not a clean T. That is like a, I don't know what you want to call it, a plus, not a T, right? So if it has, can I determine any of those zero? No, I got up force, down force. Those could have load. I've got right force, left force. Those could have load. That's not clean. Okay,
But they're all stretched.
I don't know. They could all be pointing in. I just made assumptions there just to look at the free body diagram, right? But from that connection, I cannot determine that that's zero or that's zero. No way. You're done. Your zero force member fun is gone. Okay, but look what it did. It eliminated all these members, and essentially I have one large triangle that's carrying that load. That's legit. That's probably true, right? It actually is true. When you calculate this out, these will all have load. These would all be zero if you did all your math correct. So we like to spot them. It simplifies the problem. It helps a lot. Zero force members. Cool. All right, let's take a break and then we'll work another one of these. We can work any one that you want. We can work a homework problem, which was like number 5, or we can do 7 or 8, which is your homework for next week. Whatever you want. You guys will decide. 5 or so minutes for a break. Take a breath. Oh, don't stop recording. I don't want to stop. I want to pause. Almost. Number 8. Method of joints. All right, I'm going to get my loads in. 10K. No, method of sections. We would not want to do this by method of joints. That would be a little bit brutal. Got a roller at F, that gets 1 reaction. Fy. And a pin at A. And that gets 2. AY and AX. How far apart? 10 feet on these bays. What's going on over there, Todd? And 9 feet tall. Yeah, do I have that all written down correctly? How's your truss looking, man? Is it off your? Yeah, I had poor planning too. That's just poor planning is what that is. Where's my AutoCAD so I can just move it around, right? All right. Good, good. Same process in the beginning as method of joints. You have to find the reactions first. So first step actually would be, is this a truss or is it a frame? Because we need it to be a truss. So it looks like it's built out of triangles. That's good. Straight members. Yeah, looks like it. Loads are all at the connections. Yep. It's definitely a truss. Okay. Now we need AY and FY, the reactions, and AX. Anyone see what AX is equal to? Are there any X loads? Any external X loads? Nope. AX is equal to 0. So at this point, the truss is connected. It's all together. I don't look at the inside guts at all yet. When I finding those reactions, I just use the external forces. So this is back to like chapter 4. How do I get AY and FY? A moment.
The distance. Top to bottom
9. Where do you want to do the moment at? Anybody? A. Why not? We're a very left to right society. What are all the moments about point A? 10K times 20 feet. Rotation is negative. 6K times, yeah, because it's probably halfway, right? I don't know about 15, but I like the 5 part. How far is it from 6K to point A? Six K is here. 25. Negative rotation, same rotation. And then 8K times 35 minus. And then FY times 40 plus. Set it equal to 0. Again, poor planning. You'd think after 30 years, I'd be able to get an equation on a piece of paper, but I still can't do it. And we solve for Fy, it's positive, so we leave it here. All these negatives go to the other side, become positive, so I'm liking our Fy number. It's going to be the correct direction. Somebody check me on this. Okay, let me catch up.
So we've got all the
Reactions. Yep, got the reactions. That's our, after we determine it's a trust, the plan is to go for the reactions. The old method would say, method of joints would say, hey, start at a joint and good luck. Like work your way across. So people said that's nuts. We need another way to do this because we really don't need to know what every member is. We just need to know where the largest loaded members are, right? So after you've done this for a while, you kind of get some experience and you know, hey, those largest loaded members are usually somewhere in the middle of the truss, right? So we need a method to like zero in on the one we want, right? So this problem said, determine the forces in members CD, DH, and HI. Right? That's what the problem said. Hey, we want to know just the members in those, the force in those members, not the whole damn thing. Because one of these is going to be like the largest loaded member, right? So we have a method for that, and it's not the method of joints, or you'd have to go from here to here to here to here, to here, you know, it would just, it's time consuming. It's crazy stuff. So when they ask you for this, sometimes they'll give you the three members that are kind of in line. Like these are in kind of line, right? And what we're going to do is we're going to section the truss. We're going to, because the whole thing's in equilibrium, right? Whole thing's in equilibrium. Any piece is in equilibrium. This piece, that piece, this piece, all in equilibrium. No matter how I chop this thing up, when I redraw it, it'll be in equilibrium. That's the rule, right? So when they give you those three, what you're looking for is you're looking to draw a cut line through the truss. That cut line can only cut through three members. So if you get a complicated truss and you're going to cut through more than three, you can't do method of sections. Like you just can't do that. That would give you more than three unknowns. And we have three equations because this is going to end up to be a non-concurrent problem. All the forces don't go through one point, so moments come into play. So we get three unknowns. All right. So when you do your cut for method of sections, make sure you're only cutting through three or less. You can cut through less, but just not more. When you cut through it, those members that you cut through become forces, and you draw the truss to the right or to the left of your cut. Doesn't matter. Left side. So in other words, I could draw that truss and work this problem. Or I can draw this side and work this problem. Either one, you're going to get the same answer if no mistakes are made. I usually choose the one with a little less going on, like, oh, there's a whole bunch of trusses. I mean, a whole bunch of forces over here, 6, 8, FY. I'm not going to use that side. I'm going to use this side. It's a little simpler. But again, it's not going to matter. So where you cut through become forces. All this goes away. This stands alone in equilibrium. I definitely redraw it when I do these problems. So now I'm going to redraw the truss that is what is still together. So this, all of that is still connected. That's the truss that I'm going to draw. Method of sections. And again, you put everything in that you know. And that hits this part of the truss. And what you cut becomes vectors, and we just put them all in tension because there's no way you'll ever know what they are. Oh, thank you, sir. And just like method of joints, once you get your new truss drawn, you no longer need that other pieces. So these members are in here, but they don't really matter because I'm leaving all of this together. I'll draw them in though, so it's not too confusing. So I cut through CD, HD, and HI, right? Cut through the ones they want to know. And I turn them into vectors, and I put them all in tension, all pointing away from the joint. just because there's gonna be so much going on that you're not gonna be able to determine it. You're gonna have to let the math do it for you. Okay, and then I put in everything else that I knew. 825, I knew, 10K going down here at point H. For sure. All right. I would definitely want to dig out this angle because I'm gonna need this angle. So I'll get that next. And that is gonna be, this thing is 9 tall. Yeah, 9 tall. So if I use this triangle over here, where this is 9 and halfway is 5, I should be able to come up with that inverse tangent. 9/5, right? It's just like I was doing it over here, where that's 9, this is 5, same kind of thing. That is a rapid prototyper. At least that, if that's what you're talking about. 60.945. Huh? You got 9 here and you got 5 here. So I just did tangent of the unknown angle is 9/5. So then it's tangent minus 1, 9/5. Non-concurrent force system. Actually, we've done a bunch of these. It looks a little different because it's like a truss thing. Gonna get rid of some of my scratches. So the way to do these is just like we did method of joints, is you want to think about the direction that has the least variables. So think about how many unknown in the X, how many unknown in the Y. Maybe we can solve something. Anyone see any direction that's interesting? All right, let's just talk through all the forces in the X. What are they? HI is all in the X. What else? The component of HD is in the X, correct. What else? Anything else in the X? Is 10K in the X? Is 8.25 in the X? Is CD in the X? Yes. HI? Yes. And the component of HD? Yes. 1, 2, 3 unknowns in the X. Good luck with that. I'm not doing that. Let's look at the Y. Is 825 in the Y? Yep, and it's known. How about 10? Yes, and it's known. How about HI? No. CD? No. What about the component of HD? Yeah. And it's the only unknown, 825 and 10 and HD. Why? Good. So I'm going to write that equation. Some forces in the Y plus 8.25 minus 10K. Probably going to have to go up plus HDY, the component of HD. And that's got to be equal to 0. Anyone else get that number? Good. All right. So now I know the y component of HD. I'm going to actually draw HD out here. And I'm going to draw it over and up and 1.75 is that y component. Right? So I just pull HD out. I know this angle, 60.945 degrees right here. And I want to know HD. So I know the opposite. I don't know the hypotenuse. I do know the angle. So that should mean opposite over hypotenuse is sine. So I'm going to say sine 60.945 equals 1.75 over HD. HD equals, these switch places. Okay. Compression or tension?
Well, it's positive, so it's pressure.
Nope. Positive does not determine compression or tension. Does it point away from the point or to, yeah, so that means it's in tension. So when this came out positive, HDY came out positive, that means our direction's good, right? This does have to go up to fight the 10K going down. The 8.25 needs help. So that's got to go up. So this goes up and away. Definitely tension.
HD, away from the point, it's 2K.
HD is going away from the point. It's 2K. It's in tension.
How would it be stretching?
You mean conceptually, how is this in tension? I have no idea. It's a truss. Loads go all kinds of directions. So that's why I have to rely on my math. How that's in tension. Yeah. Don't know, man. I mean, that if you can explain that one, then that's pretty trippy because forces are going all kinds of directions inside this truss. Yeah. So we got one of them. That's good. That's excellent. Now we have still got two unknowns, right? These two, and they're both unknown in the X. Still don't know them. I know this X component, or I could figure it out, right? But I still have two unknown in the X. So it's not going to do any good to write the X equation. You're going to end up with two unknowns. What was our third equation? Moments. We need to do a moment on this creature. Yeah, so do it where you can eliminate a whole bunch of stuff. So point H right here is a great spot to do your moment because HI drops out. And that's what we want. We want one of these to drop out. So this is a great spot. You could do it here, but you got to include all of these moments if you do it up at C. So C is not a great spot. So let's do a moment at H. Here, I'll even scoot it. Oh, no, it'll be fine here. So my notation, summing the moments at H. So I'm positioned here. It would be 8.25 times 20 feet. That distance right there. And the rotation is, because I'm doing moments, the sign needs to be, careful, positive or negative. What is that rotation? That's clockwise, negative. What else creates a moment about this point? CD times what? 5. This distance right here, 9 feet. CD, making the perpendicular, 9 feet. And its rotation? Negative. So there's only 2, that's kind of nice. That's a good spot to pick. Moments about H, right
How
here.
come there are only 2?
How many forces are on this truss? Actually, there's 1, 2, 3, 4, 5, right? But if I do moments here, what drops out? Anything that goes through that point drops out when I do moments. So drop out, drop out, drop out. That means I only have these 2 creating rotation about that point. Now we got to solve for CD. So this moves to the other side, becomes positive. This stays negative. So we're going to end up with a negative number. What does the negative sign mean? What does that mean? It means CD is going the wrong direction. That's what that sign means. Anytime you come up with a negative fourth, that means the force you're solving for is going the wrong way. That assumption was wrong, is what it means. So we go fix it. That's why we work in pencil. CD goes this way. The math is telling us that. So then I go back in here and I can find CD and change its sign. Because the rotation changes here. Right? It's going to now rotate positive, and that changes the sign here. So that means CD is going that direction, to the left. Because moments, it's rotation, right? So now this rotation goes this way. That's a positive rotation. So those signs are super important. So CD points into the point, it's in compression. 2 of them done. You got HD done. You got CD done. You got 1 left, HI. But we know this one, and we know this one. How could we get this thing? Sum the forces in the X. Yep. And that will be your homework on this problem. We just worked 99% of the problem, Ben.
Yeah,
But what? Yeah, but.
yeah.
Work your way through it. You got 1 equation left, some forces in the X. That is method of sections. So I think your homework is 7 and 8. So 7 is back to method of joints. So yeah, you get to do both.
Oh,
But we just worked 99% of this one, Ben. So
It's fun. It's fun when you're doing it in class, but it's not fun.
yeah, welcome to the world.